is Roselyn, and I'm going to be taking you over the design overview and our design for the heat engine project. So the idea behind the heat engine project was to use to our advantage the rise and fall of a piston as you put a canister in cold and hot water. The first data that we collected for this project was to give us an idea of how much mass that you put on top of the piston and how long it would take for us to complete a cycle. And as you can see, increasing the mass most definitely increase the time that it would take between one rise and one fall. So we decided to take this idea into consideration for whether we were going to rest our mass on the piston or use another system to hold the mass. Cut. I like that one. So with our design, we wanted a system that would not put too much weight on the piston, but would also take advantage of the rise and the fall of the piston as you changed between the hot and cold water. And the best thing to do that for us was choose the ratchet system. We have two arms that will interface and interact with the teeth, and as you go up, one side will slide down while the other side pushes, and as you go down, one side will push while the other side slides down. And with this continuous movement, we had about 26.67 centimeters down there, and that's what we hope to use. We would be attaching a mass on top of this, so that's where our mass would hang, and then with each sort of rise and fall of the piston, our mass would be stored instead of coming down. Yeah. So from our design, we realized that we'll be able to get 26.67 centimeters of height, and our target mass to carry was 50 grams, which is 0.05 kg, and all that would mean that we would have a target stored energy of 0.131 joules. But when we actually did the experiment, we were only able to carry a nail that was about the size of 3.75 grams, which is 0.0375 kg, and we were only able to raise it a height of 1.5 centimeters, which altogether gave us an actual stored energy of 55.2 millijoules. And that means that our design was only able to do about 0.42% of what we had expected.
Shown here is the PV diagram of the piston. Before we started, we made a few assumptions. The first is that the piston does not leak and there is no gas escaping the system through the tube. Therefore, the mass of the gas stays constant. We also assume that the temperature in the water baths is evenly distributed. We also assume that the processes are adiabatic and that the processes are slow. The can is not well insulated. For process 1 to 2 and 3 to 4, these processes are isochoric. The volume doesn't expand because the pressure of the gas is less than the gravitational force exerted onto the piston by the engine. The volume doesn't change until pressure is high enough to counter the gravitational force in process 1 to 2 and is low enough in process 3 to 4. Processes 2 to 3 and 4 to 1 are isobaric. The expansion process is slow, so volume is constant. In process 2 to 3, pressure is constant and it is equal to the mass of the engine and the mass of the piston times gravitational force divided by the area of the piston. The temperature increases until it reaches its highest maximum temperature, which is when volume reaches its max. In process 4 to 1, pressure is constant as well, and it's equal to the mass of the piston times gravitational force divided by the area of the piston. The piston contracts until temperature reaches its coldest possible temperature, and it's also the minimum volume that can be reached at this point. This is a table of values that we are using to calculate our total work in the system. To calculate the total work done by the heat engine, we determined that work is change in pressure times change in volume. Because processes 2 to 3 and 3 to 4 are isobaric processes, we determined that work is equal to the equation shown here. We know that the volume at 3 and the volume at 4 are equal, and the volume at 1 and the volume at 2 are equal. So we were able to plug in these values and determine that the total work is equal to P2 minus P1 times volume 3 times volume 1. Using the values that we showed in the table and the equations that were just shown, we determined that the total work would be 2.80 joules per cycle. There we go.
Just want to
It did move up slightly.
So when it came to final testing out our final product, we found the calculations and timings from the design brief obviously were not perfect. We had initially thought that we'd be able to raise the mass every time that we transfer between the hot and the cold baths, which turned out to not be the case. And we only were able to test for about 3 out of the 5 minutes before the arms got stuck in the teeth and nothing would move. So for the vertical component, we made it just way too tall. We failed to realize this when we were designing it, but we wanted to make it as tall as possible to store as much potential energy as possible because of the extra height. So we used the whole entire length of the sheet of MDF, which is 24 inches, a quarter inch. So it turned out to be very heavy and just added a bunch of extra pressure to the piston, which didn't allow for as much movement, and we were only able to raise it about 1.5 centimeters, which is definitely not as high as we thought, because we were planning on the piston moving up and down and then the vertical component rising every single time, which was not the case. At first, for the vertical component, we didn't account for the shifting that would occur with only one dowel. So with one dowel, it would just rotate about that, and then it wouldn't move. So we added a second dowel for increased stability, but this increased stability also limited the motion, so it'll only be able to rise a few inches before it would just stop. For the arms kept getting jammed in the teeth, which kept meaning that we had to go in and move them with our hands, which was very inconvenient. The arms also frequently moved off the axis where the teeth are located, which meant that we had to go back and fix them and fix the bands that were holding them in place. We realized that we should have shaped them better so that they fit into the teeth, and that would have helped with the jamming, because as we were testing, we had to keep filing them down so that they fit better in the teeth. So I think filing worked fine, but if we had gone back and fixed the actual design and shaped them to fit in the teeth better, I think we would have been able to raise the mass a little bit higher. So we also were not able to follow the timeline as closely as we had wanted to, and ended up doing most of our testing the day of the lab. So I think that if we had selected the timeline a little bit better, that we would have been able to go back, test earlier, and then we would have been able to fix what needed to be fixed, and we would have been able to perform a little bit better in lab. But I think overall we were able to make it move, and we're happy with that.